So welcome to the last tutorial of ACT. Today we are going to talk about monads and comonads. I suppose that this is the talk that will need a little bit more background compared to the three previous talks, but of course you're always free to ask any questions. I will stop for questions, like for live questions to me, but in the chat, you can always feel free to ask whatever is not clear, okay? So let's maybe get to it already. Monads and comonads can be seen as particular functors with extra structure. And we're not going to say what they are in general. I mean, we're going to give the definition, but then I want to give you some flavors of some ways in which these structures come up in practice when you work with them. Not always. So I'm going to give you some examples of how it's likely that a thing looks like when it's a monad or a comonad, okay? So let me already tell you, most of the material that I'm going to present here is taken by some lecture notes that I've written, which are in here, they're in the archive, in particular chapter 5. Some further references on the stuff that I'm going to say are the book of Emily. So if you were here in the previous tutorial, this book was already mentioned. So in chapter 5 in there, you have a lot of material on monads, much more than you can find in my notes. And especially for the ones that are more like programming or computer science minded, I suggest pretty much anything written by Bartosz Milewski. He has a book as well as a blog where he explained these things very well for computer scientists. All right, so let's get started. What is a monad? Okay, let me give you the rigorous definition, like the dry definition, but almost immediately let's try to see how we can interpret that, okay? So if C is a category, a monad it's usually denoted by T, mu, E on C is, first of all, a functor from C to itself. And then we have two natural transformations. So eta, that should be from the identity to T, which means that the component are going to look like this. So if C is an object of C, we have C to TC. A natural transformation mu. So in components, this would look like this. These are sometimes called unit and multiplication. For the German speakers, eta is for Einheit, so unit, and mu, which is multiplication. Such that the following diagrams have to commute. So let's say for every object, we have that this triangle commutes. So here we can apply eta of TC. And this is the identity. We have that this triangle commutes, where this time we apply T to eta SC. And this diagram commutes. There are a bunch of T's. Yeah. Okay, now this is very dry. So what is this good for? Okay, this is good for very, very, very many things. But here's one that usually comes up, especially when you do something that involves either programming or probability or type theory, or these contexts which come up a lot when one does applied category theory in the sense of the conference that's about to start. So here's the idea. A monad is a way to extend our spaces to allow for extra outcomes. Okay, so very, very monads, very many monads that appear in practice have to do with extending our spaces, because you want to have either like more generalized elements or functions with more general output. All right, so let's first see an example, maybe a couple, to see what does it mean that we extend our spaces and what that implies. Okay, so first example, the power set. So that's a monad in the category of sets, okay? Set, which is the category of sets and functions. What's the idea? First of all, take a set. Maybe let's give colors to these elements. This is small x, this is y, and this is z. Okay, so you take a set and you want to form the set of its subsets, okay? So we call px a set whose, maybe let's do it even larger, a set whose elements are the subsets of x. So the subsets, the elements in here are the empty set. Then there are going to be 3 singleton sets, one for each one of these points. So the set only containing little x, the set only containing little y, and the set only containing little z. Then you have sets of 2 elements. So these would contain all possible subsets, and of course there's again the set containing all 3. So what does it mean that we have expanded? What does it mean that we have expanded our original set? So first of all, let me notice that, so Px is a set that does not see inside the little set. We don't see there. It just sees the set. So Px is a set in this case of 8 elements. So this just counts as 1 element. This does not count as 2, okay? But in which sense does Px extend x? Well, the idea is that it's as if we could embed this set as a subset in here, where each point is mapped to the subset containing only that point. Okay? So there's a map from X to Px that, given an element, associates to it the singleton containing the element. Now, clearly, we can't really say that an element is a subset. Like, I mean, if you want to be like really precise, an element is not a subset, but of course it defines a subset, a singleton subset, a subset of only one element. Okay? So in this sense, the power set includes the whole set and allows for extra things. Okay? Now, why may we want to extend our original set to have extra outcomes? Well, suppose that you're having a program that wants to compute as results the elements of X, and this program may not terminate for whatever reason. Or maybe the problem that you're trying to attack has no solution or has many solutions. Okay? So the result, instead of just being an element of X, could be more generally a subset of X. So this accounts for the case where you can have no results or multiple results, which in practice arises all the time. So there are lots of things when you work in practice where the outcomes are not uniquely determined. Okay, and here is how you can talk about subsets as outcome in a way that doesn't break all the theory. So let's see a little bit more the monad structure of the power set. So first of all, we want a functor, right? So P has to be a functor from sets to set that, okay, given a set, we find Px, which are the subsets of X. Now, what does it mean that we have a functor? It means that if we have a function here from some other set Y, of course, Y will also be mapped to Py, so subsets of Y. Then the fact that this is a functor means that we also need a map here. That's usually denoted by PF. How does this work? Okay, suppose you have the set X and the set Y. And the function f maps, let's say, this here, this again here, this here, and this here again. Let's say it goes here. Okay? Now take a subset of X. We have to map it. Okay, let me maybe draw it inside X so you see it's a subset. Okay. We have to map it to a subset of Y. You see, there's a very natural way of doing so. Just take all the elements in this set and follow the arrows. You see, you'll land in this set here. Because these two elements both go to the first element, and this extra element here will go to this one. All right? So this is sometimes denoted by the, called the image. Okay? So if A is a subset of X, then this set down here is usually called just simply f of A. Okay, so if you remember what was happening in Emily's tutorial, sometimes you don't write the P because it's pretty clear what the operation is going to be. All right, so in set theory, you usually just write this. Like if you give as an argument to this function a set, it means just apply it element-wise. If you want to stick to like a standard and completely strict category theoretic notation, then you can write a P here. Okay, so that's the functor. Of course, for those of you who are not that familiar with functors, you may want to check that this assignment on functions preserves identities and composition. Okay? Now, moreover, we have a natural transformation, eta. So what was eta? Let's go up here. Eta was telling us that an element of X defines a subset of X canonically. Okay? Okay, what does it mean that this is natural? Maybe let's stay here to draw the diagram since I have space. So what does it mean that this is natural? It means that if we have a function 2i, and now we do the same here, so here we put pf, okay, which just applies f element-wise, as we did here. All right? What does it mean now that this diagram commutes? Well, this means in some sense that just as px is kind of an extension of x, then pf is an extension of f to this larger set, by which I mean the following. So suppose you have this element x. Now what you can do is, well, map it to y using f, and you go to f of x. That's an element of y. And so we know by eta this defines this singleton subset of y, the set containing only f of x. Or we could have first mapped this x to the singleton, and now applying pf. What was pf? That just takes a set and applies f to each of the elements in there. There's only one. So apply f to x. What do you get? F of x. This commutes. So why is this saying that pf is extending f? Because this is saying, okay, pf extends f not just to elements, but to subsets of x in such a way that it agrees with f on the elements that come from eta. So on singletons, pf has to agree with f. All right? We have maps defined at this level. We extend them to this level in such a way that the stuff that we had already counted is not going to have any surprise. So on the old elements, so to say, on the non-extended things, we just do whatever we were doing before. Okay? So that's naturality of the unit map. So we have a functor, we have the natural transformation from the identity to P. And if you remember, there was also the multiplication. There was going from PP to P. Let's look at this. So again, let's take, maybe let's take a set with more elements this time. So now we want to map from PPX to PX. We want to map from PPX to PX. So PX are subsets of X. Okay? PPX are subsets of the set of subsets of X. So these contains sets of sets. I mean sets of sets. Sets of subsets of X. Okay? So an element of PPX corresponds to, well, maybe this set, and I don't know, this set. Okay? Now these are three subsets of X. So they are a set of subsets of X. So this triplet is an element of PPX. And now, how can we just obtain a subset? Okay, starting in here, we want to get just a subset. Well, you can take their union. I mean, you could take many things. You could take the intersection, you can, but here we take their union. Okay, so take the union of these sets, which is going to be this thing here. All right. Why the union and not any other operation you can do on sets? I hope this is going to be clear in a moment when we talk about a thing called the Kleisli category. Okay, but it turns out that this is really what you want. Let's check that this now satisfies the axioms of a monad, which are these. So maybe let me copy these and show that with this choice, this works. So first of all, maybe let's do one of these, and you can try by exercise to see that the other ones analogously commute. And if it's too difficult, at the end of the talk, you can go through them together. So here, if you have a set, here I call it C, and the subset of it, what we can do here, and now look at, well, the drawing is basically going to be the very same. So you now go in TTC. So now you take the set of subsets of X, but the one given by eta, and eta was picking out the singletons. So just, there are no other sets appearing inside the set. Only the orange set is a set appearing in this collection. And now if you take the union only over this set, so there's nothing to glue like we did as we did up here, right? There's just one set. Then of course, almost trivially, the result of applying these two morphisms is the same as doing absolutely nothing. Okay? This diagram here commutes for a very similar reason, but be careful that we have to apply eta element-wise as T prescribes. So here, instead, you get one singleton for each element in your set, and so their union is going to be exactly the same. I leave it to you to figure out what this diagram says and why this commutes. The only difficulty in figuring this out is that you have to make sense of these three levels. So you're going to have sets of sets of sets. Okay, so you have to be a little bit careful with the depth of that. All right. But this is a monad. All right. Let's see why this allows us to use, in some sense, these extended sets, extended spaces, as if they were not extended. So why doesn't this extension break the whole thing? That's because you can do a construction using monads called the Kleisli category. So, first of all, the Kleisli category is a category. Objects are the objects, okay, let's say given this monad on C. The objects of the Kleisli category are just going to be the objects of C. The morphisms, sometimes called Kleisli morphisms, are going to be, well, a morphism from X to Y is defined to be a morphism from x to ty in C. What does it mean? How you can interpret it using the thing above? Well, a function with generalized output. In the case of the power set, that's the function that takes an element of x and doesn't give you just one element of y, but more generally gives you a subset of y. Okay? It allows for these like extra effects. It may be a function with, so to say, no result or multiple results, for example. All right? In order for this to be a category, we want to specify how we can compose things and what the identities are. So what are the identities? So we want the Kleisli morphism from x to x as the identity. So that has to be a morphism from x to tx of C, right? Can some of you tell me maybe what kind of morphisms we expect to play the role of identities? Okay, someone is saying eta of x. That's exactly the case. Yep. And we need composition. Okay, so if we have a morphism, well, a Kleisli morphism from x to y, and a morphism from y to z, how do we get a morphism from x to tz? So that's a bit involved, but what we can do is, okay, let's give names to this. This is k and this is h. So now we have a map from ty to ttz given by th. You know, just apply t to this. Now we're in ttz. We have to go to tz, but here we have the multiplication, and that takes us to tz. Now this is a bit formal, so let's see what happens in the case of the power set. So for the power set, the Kleisli morphisms are the relations. So remember what is a relation between two sets? If you have a set and another set. So what is a relation? Usually when you have a function, then to one element you just assign only one element. That's usually what a function does. In a relation, on the other hand, to one element you can assign many. This point is related to 2 points. And I don't know, this point is related to nothing. This other point is related to, I don't know, 1 point, and so on. So you don't have uniqueness of the result. So that's exactly morphisms of relations. So now, suppose that you have, let me just make this a bit larger. Suppose now you have 3 sets, and you have a relation between these two, which you can view as a map from x to ty, right? From it assigns you to this, to this element, this subset, and so on. Now, and the relation here that assigns, for example, to this element, these two, to this element, these two, and to the rest, nothing. No, okay, so you see that there is a composite relation. We would really like to say that, for example, this point right here is related to these two. And that's indeed what the Kleisli composition will tell us. Okay? Why? Because we're saying, so remember, if this is K and this is H, then we apply T here to get TH, which means what? T means, again, apply whatever comes after element-wise. So to all, let's say we start with this little x, K maps it to these 2 points. So to this set. And now TH applies H to these 2 elements. Now H to this element doesn't map it anywhere. I mean, maps it to the empty set, so we don't care. To the first element, it will map it to this set right here. Okay? And if we take the union of all the set that we get this way, so in this case we get only one, but suppose that, for example, this point were mapped also to something that's non-trivial, let's say to here, then we would have gotten 2 sets, and applying mu gives us their union. Okay? That maps an element of X to a subset of TZ, the subset of all the points of Z that can indeed be reached by this composite relation. Okay? You see, from this X, you can go all the way to this point, and the same is true for this point, and now that I've added this extra orange arrow to this point as well. Okay? So that's exactly how relations compose. And that's why we wanted the union. The union has this idea of all the points that could be reached. Why the union? Well, because you have to take the paths that go through this point and the paths that go through this point, right? Some of you may ask, why is this a category? Because do the unitality and associativity axioms hold? It turns out they do, precisely because of the monad diagrams. So again, it's probably a good exercise. And again, if you find it too difficult, at the end, we can go through that together. Show that associativity and unitality follow from the monad diagrams. Okay? Okay, we are a little bit later than half an hour, but I think this is a good time to stop for questions if there are any. So I haven't, since I was writing, I haven't seen all the thread of the chat. If somebody can tell me if there are some important questions which I might have missed, I'll be very thankful.
So I don't think you missed too much, but I have let people unmute themselves if anybody wants to unmute themselves and talk.
Very good, thank you.
Otherwise, I'll set it back.
I have a question.
Please go ahead.
the Blackboard board 1, someone said that's the identity functor. Can you possibly tell us what that is?
Can you repeat? I couldn't hear very well.
The Blackboard board 1, someone said that's the identity functor. Could you possibly define the identity functor?
The identity functor. Yeah, so the identity functor or sometimes 1 to C is a functor that takes an object of your category and gives you the same object. And if you have a morphism of your category, it gives you the same morphism. You can think of this as doing absolutely nothing in a way. So in particular, rarely does one use the identity functor in isolation because it doesn't really do much. But it is important because, for example, in the case of monads, you have natural transformations out of the identity functor. And you see, for example, here, eta goes from X to PX. Okay, so usually you have a natural transformation goes between the application of two functors. So here it's between applying nothing and P. So secretly, we are always using the identity functor here. But it's customary never to write ID because it's kind of doing nothing, but it may be a little bit confusing to see why this is a natural transformation. But it is one from the identity functor. I don't know if this answers your question. Maybe something else was unclear though.
Well, I'm sort of confused now. I guess I don't know much about natural transformations. Like when you're saying eta maps 1 to t, you're not saying eta is a function from 1 to t. I don't know what that means even.
I see. So I think that's about the definition of natural transformations. Keep this question in mind, actually. At the end of the talk, we can maybe explain a little more in detail what are natural transformations in general. Okay?
Okay, thanks.
All right. Are there any more questions? Or anything that I said that is not clear or any mistakes that I might have made, actually? Could still be?
I have a quick question.
Please.
So what would happen if you replace this union with a different operator? Would that still be a monad?
Well, not that I can tell. So there isn't, I mean, in principle, it could still happen, right? The problem is that you would have to make sure that these diagrams commute if you want this to be a monad. And I cannot think of any other operation that would still do this, especially the associativity square right here. So the square. I don't know, maybe there are other operations that make this commute, but I'm not aware of them.
Okay, thanks. And so like the Kleisli morphism is associated with a monad?
Yeah.
It's a one-to-one association.
Every monad has a Kleisli category.
Right.
So a category whose morphisms are these Kleisli morphisms, these functions with extra outcomes.
Okay, thanks.
All right. So let me just mention a second example, which we will not see in details, unless, again, you guys want to see this in detail at the end. So this is, mathematicians tend to call this the action monad. Computer scientists tend to call this the writer monad. I guess if chemists used category theory, they would probably call it something like energy monad or something, because it models a lot of different things. So the idea is that you take a monoid. Now, if you don't know what a monoid is, or you know, but you're not very familiar, imagine just real numbers and addition, okay? Or if you're more computer science minded, strings and concatenation. Like, just write a string next to another one. Then, given a set, you can map it to x times m. All right? So this is somehow appending some extra things to your set, which you can view as extra outcomes. Why? So what would the Kleisli morphisms be? Well, a Kleisli morphism here would be a map like this, that takes an element of x and gives you an element of y and an element of your monoid, which will be a number or a string. So imagine that if you're doing, let's say, computer science, that's a program that takes the input x and gives you the output y, but also writes the string m on your screen. Or if you're doing chemistry and m is numbers, then this takes the substance x and turns it into the substance y, or of course the group of substances y, and plus a number, like that could be the energy release of that. So it doesn't just have the one particular output, but it has some extra outputs, which can be considered as extra effects. The effect of like releasing some energy or writing some output to the screen or to some kind of log file. Okay. Now, of course, I haven't told you what the monad structure of this is, but maybe that's again a good exercise. Define a monad structure from the following data. So here's a hint. From the fact that M is a monoid. So there's a map here that picks out the neutral element. Zero for real numbers, the empty string for strings, and the multiplication, which is, well, times and, plus. And strings, it's usually denoted again by plus, at least in the programming languages I know. Okay, concatenations of strings. Now, how can you define a monad structure from these two operations? All right. Okay. That's what I wanted to say about the monads. So are there any questions here about like comprehension that's better to answer now? Otherwise, I will switch to comonads.
Sorry, I just now let people unmute themselves.
Sure. So anybody has
Well, are there any commutativity diagrams that you could show?
here?
Yeah, for the.
Oh yeah, maybe that should be part of the hint. I'm not going to write the diagrams, but I'm going to tell you which diagrams they are. So M is unital and associative. That should help you.
I also had a question. Sorry if this goes into any of the homework, just trying to get the intuition here.
Okay.
Not super clear. Why is the third axiom of a monad needed? I mean,
The associativity.
That's what it encodes. Okay, or tries to capture. Okay.
Yeah.
Yeah, thanks.
Oh yeah, so maybe I should say this. The associativity and unitality of the categories follow directly from these diagrams, and they correspond precisely. So this one corresponds to left unitality. This corresponds to right unitality. And this corresponds to associativity. So It's like there's kind of like a one-to-one correspondence between these three properties. And so in particular, you need all three. Like in some particular cases, some imply the others, but in general, they don't. So in the generic case, you need all three, okay? And so an example of monads that I usually work with is probability. So that's, again, an extra outcome that is probabilistic instead of, in this case, non-deterministic. If some of you are interested, we can also see why that gives a monad. Okay, but I feel like that requires a little background in probability, which I don't want to assume from the audience. All right. So if there's no more questions about here, let's go now to comonads. So comonads, some people would say, are just a dual to monads. And that's, of course, true. And technically, we could say all the categorical part without ever rewriting anything. The problem is that in practice, we want to work with categories that look a bit like set and not like the dual of set. So comonads for us will tend to model different things, okay? So let me maybe be lazy and reverse the arrows. I shouldn't have copied the title. Huh. So what is a comonad? And usually, okay, let me leave these arrows for now. So we don't reverse the functor, okay? It's self-dual, but even if it weren't, do not reverse this. Reverse these, okay? Instead. I mean, again, the identity doesn't really need to be reversed, but okay. You reverse the morphisms and so also the natural transformations, which are defined in terms of morphisms. But be careful, the functor stays as it is, okay? Now, how can we interpret comonads? So idea, comonad is a way, oh, why am I writing so badly? Is a way of extending. Maybe this time let's say expanding, because it's a kind of different way. And this time, instead of having like extra elements or extra outcome, we want to encode extra information. Okay? Now, again, just like not every monad can be interpreted the way I told you before, not every comonad can be interpreted in the way I'm telling you now, but very many in practice seem to behave in this way. Okay? So the idea is that you have your object X and the functor part of a comonad. Let me denote the comonad by C this time. Will be, well, X, but with some more information that you didn't have before. Okay? Now, it is always free to forget that extra information. So you can always go back to C. And that's going to be the co-unit. So the map that before was dual to the unit here. Okay? And also, in some sense, the extra information can always be copied. Okay? And that gives the co-multiplication map. So as an example. Maybe now let's give the dual example to the writer monad. This time let's do this one in more detail. So the reader comonad. So again in the category of sets. So let A, no, let's call it E. E be a fixed set. So we can think of this set as being a set of extra data. Okay? Now, given any other set, we can form the set x times e, which appends extra data to x, okay? And now, we have two natural transformations. One is this one, x times e to x. Let me denote this by nu. That, well, just forget the extra information. And there's one instead that copies the extra information. Just copy it. Use it twice. Okay? Okay. Can some people tell me why these are natural? And what's the way to see the naturality of these two constructions? So I'm looking at the chat. You can write there if you want. Brute force. That also, unit dilemma, maybe. I mean, whenever someone says unit dilemma, I'm always very reluctant to say no because it may be involved instead. You never know. But so the reason is that if you have, let's look for example at the naturality of nu. If you have a map f from x to y, then if you start with xe, then the functorial part of the monad doesn't touch the extra information, okay? And so f will never use the extra information to obtain its result. So you can forget this extra information before or after applying f, since f does not really need that information, okay? And the same is true for copy. Okay. Again, what's the dual of Kleisli morphisms? Well, that's co-Kleisli morphisms. Co-Kleisli morphisms. Now, so a co-Kleisli morphism from x to y for a monad, for the comonad, sorry, is a morphism cx to y. So what's the interpretation here? This function depends on the extra data. This function has access to this extra information. All right. So let's see what that is for the case of for the reader monad, or the reader comonad. That is a function from x times e. Why did I write something like that? To y. So this would be something like, you know, x e, if this is like some key x, sorry, that's not y, it should be some e k of x e. And this depends non-trivially on e. Okay? So why is this called a reader comonad? Because just like before, in the case of the writer monad, you could have an input and there was an output and also an extra writing, for example, on the screen or on the log file. Here, you don't just have the input x, but in order to produce the output y, you also have to read the extra data e. Okay? So maybe, I don't know, your program has to first look up something from some library, or has to, I don't know the data of, or the date of today. So that the program needs some external information in order to produce your outputs. Okay? And you can imagine the Co-Kleisli composition, how is that going to be? So maybe let's instance this in this particular case. It's general enough so that you can probably reconstruct the general case. So if you have x times e to y and y times e to z, then here's what you can do. First of all, you copy this. So you have how do I do this? What's the best way to do this? Okay, we have to obtain something from x times e to z. And we proceed as follows. So first of all, from x times z, we apply our co-unit. Our co-multiplication, and we go from x times e times z. Copy your extra data. Now k comes in. So k was from x times z to y. So k times e is going to go from y times z to z. Let me call this h. And now composing all of this, we get to z, okay? So explicitly, let's make some space. This is going to be, it takes x and our x information, it copies it, and now the first two are used by k to produce a y. So, and there's, we haven't, so we can still use the other copy of e, and we use it by applying h to it. Okay, so that's, for example, a program that needed the date of today also later on in the procedure. Okay, these two parts of the program, k and h, both needed the date. And so, I mean, of course, as long as you run them the same day, the date was copied or accessed twice, and it was used first to produce the value of k, like this y, and the secondly to produce this one. Okay? Question: how do you define this composition in general? For theoretical questions, such as what is Co-Kleisli composition, of course, it is perfectly good to just reverse all that you do for monads, because that's just purely formal question. But in this interpretation, of course, this is something that you wouldn't obviously see by just reversing what you can say for monads. Okay? So it's 5. So let me conclude giving a second example of a comonad too. So what's called a string comonad. So that's again in some sense dual to the writer monad, but in a different way than the reader comonad. So take n like natural numbers with addition and of course 0 that form a monoid. You can do it for any other monoid, but I'm doing it for n because it's particularly concrete. So that's again on set. What you can do is that you take a set and form the set of sequences. So these are like some elements of these are like infinite sequences. Let's see. Infinite sequences, like infinite words of letters from your X. Okay. You may think of how this is functorial. Well, just apply the functions in each slot here. And you can think of this as equipping a point with an extra information, which is its trajectory or its history, depending on whether you want to look at this as a sequence going in the future or in the past. Well, it depends on what you want to model. This construction works for both. And now, why is this a comonad? Well, of course, you can always forget the history, right? If you start with x0, x1, and so on, well, forget where it was yesterday and the day before yesterday. Just look at where it is today. On the other hand, you can also look at the history of the history, right? So this is a history book written today. The last page talks about today. The next to last page talks about yesterday. The next to last page talk about the day before yesterday, right? That's how history books work, more or less. What is the history of the history book? Well, that's going to be some kind of matrix. And the first entry tells you how the history book is today. But that's just the first entry. The second entry tells you how the history book was yesterday. And of course, it was not talking about today. It was ending yesterday. And so on. Okay? So as an exercise, well, let's say exercise brute force, prove that this is a comonad. Sorry for the writing. It's an uncomfortable corner of the screen. A more abstract exercise. Show that this is a comonad just because n is a monoid. Okay, so if you're algebraically minded, try this way. Of course, for the application, it's better to understand this directly, like in terms of history. And again, in terms of applications, why is this important? Because, well, Co-Kleisli morphisms here are maps that have access to the history, are maps that depend on the past. In probability, I mean, of course, there's also the randomness, but especially like non-Markov processes are not just random, they also depend on the history, okay? So whenever you want to model something, sometimes its descriptions or any descriptor of future behavior may not just depend on the present state, but also on the past state. And what's happening there is that you have a co-Kleisli morphism of the string comonad. Now, of course, if you want continuous time, you may want to use like real numbers instead of natural numbers and so on. But since you're just using that you have a monoid, that's pretty general, okay? So again, you see, the feeling of a comonad in many cases is that you want to have extra information that could be forgotten or used twice, and you want your functions to have access to that extra information, to depend on that extra information. Right? Monads, generalized outcomes, generalized outputs. Comonads, larger inputs, more informative inputs. And that's more or less how the duality is, right? All right, let me stop here. And again, I'm more than happy to hear any questions.